All right. We talked on Monday about this idea of getting the slope of a curve at a particular point. And we use that by getting the slope of what's called the tangent line. Tangent line crosses through at a specific point. And so we had the slope formula of picking a point very close to where we were talking about and using the slope formula there. And we let the distance between the point get closer and closer and closer to the point we were interested in, so that the ideal would be that the point is just directly on top of the other point. But we couldn't do that, so we would hypothetically make it closer and closer and closer, and so we would use a limit. So the limit as that distance approaches 0, we're going to use h. But you'll see sometimes you'll use delta x and delta y for changes. If you see delta in I think chemistry uses delta for change as well. Sure does. But math uses it too for if you see delta, it's going to be change. So sometimes you'll see delta y over delta x. Sometimes you'll see dy over dx for change in y over change in x. But we're using h to stand for this little distance. Okay. Slope of the graph of f of x equals 4x minus 6. So we're gonna take a basic example, even more basic than the one we were looking at on Monday, and gonna find this this limit as h approaches 0. At x equals -3. So -3 is that x coordinate, so we're going to use that for c. So the limit as h approaches 0 of f of our c, our point, particular point that we're interested in is -3. -3, 18. So -3 is that x coordinate we're putting in and finding the slope at that point. Okay, hold on a second before we do this. What is the answer going to be?
-18. No, that's not right. 4.
What is the slope of 4x minus 6?
4.
Thank you. So the answer we should expect should be 4. Because it's a line, so the slope just stays the same throughout. It doesn't change. So this is a way of kind of making sure that our method of doing this is going to work out here.
Making sure calculus.
Yeah, making sure math's still working. Okay. 4 times -3 plus h minus 6. That's f of -3 plus h. And then minus f of -3. That's 4 times -3 minus 6. All over h. This is limit as h approaches 0. Here we go. 4 times -3 is a -12. So we're distributing this 4. Plus 4h. Minus 6. Minus 4 times -3 is -12 minus 6 is a -18. That's 18. If you were an astute observer, you would also notice that This should also not surprise you. The answer being 4 eventually should not surprise you. And this being negative 18 should not surprise you because it told you that f of negative 3 was negative 18 in the problem. So keep an eye out. Negative 12 minus 6 is a negative 18 minus a negative 18. All this is going to cancel out. And we are going to get the limit as h approaches 0 of 4h over h. So h's can cancel. We get 4. Surprise! It was 4 all along.
My birthday party. And it's a surprise party. Say surprise. Because that was awesome. Like semi-sarcastically say surprise, like it's not actually a surprise party. Like I knew about it beforehand, but that was fun.
All right. We have more examples that I'm not going to do right now because I don't want to spend like the 15, 20 minutes of class doing them, and then we'd only have a couple minutes left. So I'm going to jump to another. We'll do one other one.
Let's go.
But let's get the general definition here. This is the way our book talks about it. The derivative of f is the function whose value at x is the limit as h approaches 0 of f of x plus h minus f of x. So this is talking about the general function. So right now we've been finding derivatives at particular points. But we can zoom out and get a general rule. Instead of plugging in a specific point, just talking about at x, what is the more general rule that we are talking about? So this is right at the bottom of the front page where it says definition. So you're going to write down this limit. And so a couple different terms related to the derivative that I'm going to talk some more about today. First of all, the derivative is the function. That function that gives me the slope at any point. Differentiation is the process of finding that derivative. And if the derivative exists, if we can find a derivative at that point, we say that the function is differentiable at that point. And it's going to be very closely related to continuity. It's the same idea as differentiability. So we're going to eventually get specific rules for what the derivatives of a ton of different functions are. That's what we're going to spend the next few weeks looking at. But let's see how some of these rules might work and how we might get some of these rules. What I'm going to have you do on Friday is to actually go through and find what's the derivative, how do we get the derivative of x squared, and then how do we get the derivative of x cubed and x to the fourth and x to the fifth, and prove what in general, what the derivative of x to the n is going to be.
Is that the power rule?
That is the power rule. But we're not going to do that today because, again, it would take too much time. And so what I want to do is I want to jump to the example of square root of x. f of x plus h minus f of x all over h. This time we're not putting in a specific number for x. We're just generally talking about the function at x. So we have square root of x plus h. That's f of x plus h minus square root of x. That's f of x all over h. Can't plug in 0 because then I get 0 over 0. Can't plug in 0 for h. So we need some way to be able to cancel and maybe get rid of the square roots.
The power rule.
Nope. So what did we do to get rid of some square roots for limits? We multiplied by something.
Oh, conjugate.
On top and bottom. So on the bottom we have h times the square root of x plus h plus the square root of x. Not very promising for us on the bottom. But on the top, what happens is we have square root of x plus h minus square root of x times the square root of x plus h plus square root of x. So that's the difference of squares, and it multiplies together to be square root of x plus h squared minus the square root of x squared. X minus x is 0, so we just have an h on the top. And now h's cancel on top and bottom. At some point in finding these derivatives, we need those h's to cancel on top and bottom so that we can actually plug in our number that we're interested in, which is 0. 1 over, actually, limit as h approaches 0. 1 over the square root of x plus h plus the square root of x. Which means that now we can plug in 0 for h. 1 over the square root of x plus 0 is just x plus square root of x, which is 1 over square root of x plus square root of x is 2 square root of x. So this is another bit of notation here. F prime of x. So we use this little prime for the derivative. So now we have this general function for the derivative of square root of x at any point. So now if I were to find it at 1, 1, and 4, 2, instead of doing this whole limit process again, then all we need to do is to plug in 1 and plug in 4. So f prime of 1 is going to be 1 over 2 times the square root of 1. Square root of 1 is 1, so that's 1/2. So that slope at 1 is 1/2. Then f prime of 4 is 1 over 2 square root of 4. Square root of 4 is 2, 1 over 2 times 2 is 4. Done. And eventually where we'll get to is being able to go from here by like the end of next week. We're going to be able to get from f of x, the square root of x, directly to the derivative is 1 over 2 square root of x, without having to do this big long process. This big long process is showing you how the rules happen and where the rules come from. And so we're going to go through them this week. You're going to have a homework assignment where you're going to have to do this out the long way. And then after that, you're going to be starting to memorize rules. So we'll do some more of these, but not today, because I want to get through some more ideas and properties of these derivatives. Actually, maybe we'll do this one. We'll see how much time we have. But I want to make sure, first of all, that I give you this. This is the first homework assignment. You need even after later this week and next week when I show you the rules, I am still expecting you to do these the long way with the limit. And doing that limit as h approaches 0 and all that junk. And there will be a question on the next test for one problem where I'm going to make you do it out the long way. The good news is that by that time, you'll know what the answer is going to be. So you'll be able to check your work. You'll be able to know in your head very quickly what the answer is. So you'll know whether you've done it right or not. Okay, let's continue on here. And let's talk about general properties of these derivatives. If f prime of x exists, we say that f has a derivative or is differentiable at that point x. So if we have a function that is differentiable at every point in its domain, then we say that it's a differentiable function, or the function is differentiable. Like I said, this is a very similar idea to talking about continuity. So just like we talked about holes and jumps and gaps causing things to not be continuous, those things like the asymptotes and the jumps can also cause something to not be differentiable. But on top of that, another thing that can cause things to not be differentiable is corners. So let's talk about why that is. This should be f prime of x. So here is a graph of absolute value of x minus 2. And I want you to think about what is the limit as x approaches 2 from the left and as x approaches 2 from the right. Of each of these values. So remember, the derivative is asking a question about slope. And since these are all straight line segments, you shouldn't have to do any calculations for this. From the left side, my slope is coming down this way. So what's the slope as I go from the left? It's going to be -1. And as I come from the right, the slope here is going to be what? +1. So because the limit of the derivative from the left does not equal the limit of the derivative from the right, that means that the derivative doesn't exist at 2. So the function is not differentiable.
That makes sense.
So the corners, or we can have what's called a cusp. So if we have like a straight line segment and then we have a curve like this, or if it dips down and then comes back up. So any kind of valley like that, if we're coming up like this and then we hit this point and then suddenly we start to, it's these sudden changes in the slope that we don't want. That would cause the function to not be differentiable. And one other thing here to note, differentiability implies continuity. This is going to be important. Remember when we had intermediate value theorem? And the first thing we had to make sure is that the function was continuous. So this is another way we can know if a function is continuous, is if it tells us that the function is differentiable. As soon as we know that the function is differentiable, then we know that the function is continuous. Because in order for the derivative to exist, then the function has to exist and be continuous there. But the converse is not true. In other words, it's possible for the function to be continuous at C and not differentiable. This is an example of we are continuous in this absolute value function the entire time. But at 2, we are not differentiable. But if we're going the other way, if we know something is differentiable, then we know that it's also continuous. So you'll see that come up. You'll see that come up a lot where you'll be told that something is differentiable, and then we'll say, since we know that's differentiable, it's got to be continuous. Okay. Let me look real quick. I want to pick what else I want to do with these 5 minutes here. Yeah, let's do this last example that I wasn't going to do, and now I've changed my mind and I'm going to do it. Over wherever there is a I'll just make this 2 over x so we're not confused with variables. Eventually, we're going to start to have some different variables here. But in place of x, we are going to put x plus h. So the x plus h ends up on the bottom. I don't want f of. I want 2 over x plus h minus 2 over x all over h. That is a fraction and a fraction. We don't like fraction and a fraction. So we need to multiply to get rid of the fraction and a fraction on top and bottom. What do I need to multiply to get rid of this fraction? To cancel out with the bottom here, I would need x plus h. To cancel out with the bottom here, what do I need to multiply by? Just x. So we're going to multiply by x plus h and by x on top and bottom. X plus h just cancel here, and so we just have 2x minus the x's cancel here, and we have 2 times x plus h over h times x plus h times x. Because eventually we're going to wind up with some things canceling, so I'm leaving this for now. H approaches 0 of, we have 2x minus 2x minus 2h. Over h times x plus h times x. Negative 2h over h times x plus h times x. And these h's cancel. So I have a negative 2 on top. On the bottom, I have x plus h times x. Now that I have those h's canceling on top and bottom, I can plug in 0 for h. Negative 2 over, we have an x plus h, so x times x. And x times x is going to be x squared. So that is our function for the derivative. F prime of x is going to be negative 2 over x squared. And we'll talk about why that is tomorrow. We'll get the power rule.